Right, so welcome back, everyone. Today's pre-seminar will be uh, Julius here, who will be talking about simplicial sets and cobar constructions. Take it away.
Thank you very much. Let me get right into the topic and not lose any time. So our first part of my talk will be on the simplex category. And simplicial objects. So maybe a little bit of motivation. So what is a simplicial set? You can think of it as a topological space. It is not built out of points, vertices, then edges, and then triangles, and then tetrahedrons, and so on. But we can describe it not topologically, but purely combinatorially, or in terms of category theory. Maybe a simplicial set will just be a presheaf on a simplex category. So definition, the simplex category consists of objects, square brackets n, which is simply the set of all numbers between 0 and n, where n is greater than or equal to 0, and morphisms in this category maps phi from such an object m to n, such that for all I less than or equal to j, also phi of I is less than or equal to phi of j. So monotone functions. And in this category, there are two types of distinguished morphisms. The first class of distinguished morphisms are the phase operators. So these are denoted by d and I, and they go from the set n minus 1 to n. And this map is the unique, so defined as the unique map. So monotone map such that I is not in the image of phi. So here n is greater than or equal to 1, and I is some number between 0 and n. So those are the phase operators, and the second distinguished morphisms are the degeneracy operators. And here I define, so they are denoted by, okay, I don't want to use the notation d but delta, and here I want to use sigma in I. Now this goes from n to n plus 1. And this will be the unique monotone map such that the pre-image of I contains two elements.
Sorry, so this
Yeah.
delta and sigma, they depend on phi, or
They depend on. No, so
Yeah.
phi is just a generic morphism in the category.
you mean image delta?
Yeah, sorry. Thank you. Yeah.
Constant function of functions.
Yes.
So help me, why is this unique? delta IM.
So I will draw a picture. So for the phase operators, we imagine we have a map from this object 2 and then to the object 3. And then I can draw the how this phase operator D2 looks like. And so you'll see if I want to yeah, okay, there's something missing, you're correct. Let's add injective. And here let's add surjective.
So I guess you want n
Yes.
minus 1 instead of n plus 1 as the
Here?
target?
No. Would be correct.
But you can, yeah.
No, the pointer so goes from n plus 1 to n. Thank you. Yeah. And that's the problem with these simplicial sets. It's not so difficult, but if you want to write it down precisely, then it's just easy to mess up. But in this case, it's good to have a attentive audience. Okay, now this is the phase operator. Maybe let's also draw us one of the degeneracy operators. So this would be sigma to 1. So I map from the object 2 plus 1 to the object 2, and I hit the number 1 twice. Okay.
The delta I and create like an extra point at the I spot, and the sigma removes the I, or like removes
Yes.
the I points, I guess.
So you think about it, it's not so difficult, but it's sort of not so easy to write down precisely. I cannot. Okay, now an observation. Every morphism in delta. Okay, I didn't say that this category is called delta. Can be written as a composition of phase and degeneracy operators. This will be important for the next definition, namely what is a simplicial set, or more generally a simplicial object. So let C be a category. Then a simplicial object in C is a functor from delta op. So it's a contravariant functor from the simplex category to C. Okay, this is a very short definition. Now to understand it a little bit better, I have the following theorem. So let me fix a sequence labeled by non-negative integers of objects in C. Together with maps DIN from X or morphisms rather So morphisms to x n minus 1 and s n I from x n to x n plus 1 such that, okay, now I'm not sure if I want to write this. Maybe let's skip this. So let's just write that certain simplicial relations hold. So for instance, let me write on one. I want that di n plus 1 circ dnj is the same as din circ d n minus 1 j minus 1. So for instance,
Is relations between the
yes.
delta thickness that holds.
So the point here is, by this observation, you can write any map as a composition of these face-integral degeneracy maps, and then you need to think hardly about what kind of relations between them exist. But you can write on a complete set of relations, and then to define a functor, it's basically sufficient to have a sequence of such elements together with face-integral degeneracy operators that satisfy these relations. So anyway, then exists a unique simplicial object with x of n is xn, and well, x of delta ni is d ni, and x of sigma ni is s ni.
You explain why you needed
So this is just a convention. So a simplicial set is by definition a functor from the opposite category. If you would take the category itself, then you would get what is called a co-simplicial set. But you can also do that. Okay, now let's look at some examples. So if you know some category theory, then the easiest functor from a category to set you can write down Hom functors. And so you use this some functors to define the standard n simplices. Those are just the homomorphisms in the simplicial category from, so the first is variable and then to the object n. And you can picture this, if you want, as such a simplex. So this would be a picture of delta 2. Okay, now I've drawn some picture. Let's make this more precise with the second example. Well, the first part of this example is not really example for a simplicial set, but rather how to geometrically realize these standard simplices. Maybe I define the geometric realization of this standard n simplex as physical simplex. So the set of all x0, xn in R plus 1 non-negative, such that they sum up to 1. And for a morphism from M to N, in delta, I let So the thing is, any monotone map gives me a continuous map from these geometric realizations, and they are defined as follows. We go from delta m to delta n, and this maps such a tuple to there. This is the standard basis of R plus 1. So every morphism in the simplest category gives me a continuous map. And so now, using this, I can associate to any topological space X a simplicial set. This works as follows. We'll let X be a topological space. Define a singular simplicial set of X as the following functor. So this starts at the simplest category op. Then I do this geometric realization functor to the category of topological spaces. Here it's the opposite because this is a covariant functor. And then I apply the functor of continuous maps from an arbitrary topological space to X. How much time do I have? Thank you. Okay. So maybe more explicitly, so what are the n simplices of this guy? Those are just continuous maps from the geometric realization of the n simplex to the topological space X. And if I have a morphism in delta, then the corresponding simplicial operator from the m simplices of X to the to the n simplices is given by I take a continuous map from delta m to X and pre-compose it with phi. Okay, now maybe I skip the details on that, but if you have any simplicial set, then you can build a chain complex and a co-chain complex out of it. Maybe the n chains in this chain complex are spanned by all the n simplices, and then you can write on a differential using the phase maps. Or maybe I skip this to get to to cobar constructions. So let's use a new blackboard. The cobar construction. So what's the point of this construction? So I've given you the definition of simplistic sets, some examples. But now I want to give you a general procedure to generate simplicial objects in a given category. And And the datum you need for that is what is called a comonad on a category C. So let me define what that is. So a comonad on a category C well, it's a comonoid in the category of endofunctors of C. So what does it mean? This is a triple. Okay, I use again delta. But this probably doesn't hurt. Where T is an endofunctor, then delta is a natural transformation from T to T applied 2 times, and then epsilon is a natural transformation from T to the identity functor on C, such that all objects C and C, the following diagrams commute. So what I can do is I can start with TC and then look at the component of the natural transformation delta to get to TTC. But when I'm here, I have two possibilities. Either I can apply the natural transformation at TC to get to TTC, or I can apply T, so the functor, to the component delta C, and this should commute. And secondly, if I start with TT, if I start with TC, do the natural transformation delta, then do T epsilon C. This should give me the identity. And similarly, T applied to epsilon, the component TC, should also give me the identity. Okay. Still be what's this? Okay, now comes the bar construction. So if I have such a comonad, I can construct a simplicial object from any object in the category C. So let this guy be a comonad on C. And C an object. Then the sequence T applied n plus 1 times to C, where n is greater than or equal to 0, together with the phase maps DIN from Tn plus 1 C to TNC. Yes. Where I apply the I times iterate of t to the co-unit component of E n minus I C. And the degenerate C operators are given by this map from Tn plus 1 C to T minus 2 C. I apply Ti delta T n minus I C. And this is a object, Simplicial object in C. Maybe this might be a bit opaque, so let's look at an example. Let G be a group. Then I can write on a comonad on the category of G sets. So I take any G set M and map it to the G set G cross M, where here the G action on E prime M is simply given by acting only on the first part. Then I claim this is a comonad, and with this monadic co-modification, if you want, from GM to GGM, this just sends GM to this guy inserting a 1, and epsilon M is given by the action. Any time left? Oh, okay. 2 more minutes be enough. And so now let's look at the phase and the generality operators of this guy. So here, B and I of G0 up to Gn M, I define as G0, G1, and then I multiply Gi and Gi plus 1. And when I'm at the last entry, I multiply Gn and M. Or maybe it's like this. So this is when I is less than n, when I equals n. And here the degeneracy operators applied to such a tuple inserts once. And it inserts a 1 in front of the I spot. Okay, last remark. So I have a functor from G set to set, which takes a G set M and maps it to the orbit space. And now if I set M as the trivial G set, then I get a simplicial set by first applying this cobar construction from monad T to the trivial G set. This gives me a simplicial G set. And then I apply this G in invariance functor, and this gives me a set. And this functor is called the nerve of G. Maybe so. Yeah. Oh, I mean, let's stop here. Okay.
Questions?
Thanks. I got a bit confused with this, sorry, example number 2, which is now on the blackboard that's covered, the middle one. Yeah, so with number 1, I think I got, right? So the simplicial object is a functor from this category delta or delta op, and right? But then this, so then you have this geometric realization, and that is again a simplicial object.
So this is just preparation for this example.
Okay. Yeah. I see, because you said for phi a morphism between M and N, and then you had some morphism phi with the bars. So I thought that there was some sort of functor that you defined, but that was not the case.
But your question is not wrong entirely, but you can think of this geometric realization functor as a co-simplicial set. It's just it's a functor from the simplex category to topological sets, but it's a covariant functor.
But for each n, I get one such functor, right? Like delta n is such a simplicial object, so for each, so delta n for each.
No, here the thing is not for each n, but you get a functor from this simplex category to topological spaces.
Okay.
Not for each n, but this is just the value of yeah, okay, maybe it's also a bit confusing how I have written it down. So I also would have written this, but I think this is more common. And you think about this as geometrically realizing this simplex.
Yeah, okay, thank you.
Other questions?
So hi Julius, maybe can you hear me?
I can hear.
Yes.
Okay, so maybe I have a very, very basic question because I don't know much about monads and comonads and these kind of things, but to me it looks like comonads somehow are a kind of categorification of the notion of coalgebra. Is it correct somehow?
It's entirely correct, and you mentioned it. So if you have any category C, then you can look at the category of endofunctors. So this is a monoidal category where the monoidal product is given by a composition of functors, and a monoidal unit is given by the identity functor.
Okay.
And now a comonad is simply a comonoid in this category.
Okay. And I guess that the notion of monad should be somehow the categorification of the notion of algebra. So you're able to build up this kind of cobar construction on these simplicial sets. Can you do something similar on monads? Some kind of bar construction, I guess, right?
Yes, indeed. But again, if you do it with monads, you will get a co-simplicial object.
Okay.
Yeah.
Okay. And maybe No, I mean, this is not a very well-defined question, but can one say something about some kind of analog of homology groups in this kind of cases?
Analog of homology group.
I
So
mean,
that's something I skipped. So if you have any simplicial set X, then you can define a chain complex as follows. The n chains are given by the span, where case any commutative unitary ring maybe of all A in Xn. And you can write down a chain mod or differential as follows. You map such an n simplex to some I equals 0 to n alternating sign, and then you apply the ith phase operator to A. And what you can check is that this gives you a chain complex, and then you have a homology theory for simplicial sets.
Okay, I see.
And if you apply this construction to the singular simplicial set of a topological space, this is precisely the singular homology of your topological space.
Very nice. Thank you.
Okay, maybe one more quick question.
Okay, so I had actually a very similar question. So is it also possible to understand like co-algebras as special cases of co-monads if you take just the category very small? For example, you take just one object or something, and then this choice of a functor with the delta and epsilon, would this be just the information of a co-algebra?
So question was if you can recover co-algebras in the algebraic sense as
Yes.
Yeah, there's a kind of equivalence. So yeah, you can take a co-algebra. Let's say over K. And then you can look at the functor C tensor over K blank. And this is a comonad. Okay, no, I'm not 100% sure, but if you have a okay, probably not every comonad on the end of functors on K modules is of this form, but if you know that your comonad is a functor of the form M tensor K blank, then you know that M is a coalgebra.
Okay, and in this context, how do the simplicial objects look like? Do you know this? Probably something similar to the example that's written here with the group, right? Because it's also just something G cross M.
Yeah, this should be sort of dual to the standard resolution you write down for K algebra. Yeah.
Okay, thank you.
I think that will thank Julius again. And